What if I told you that reality as you know it, the smooth, continuous flow of existence you've experienced every single day of your life, is actually a lie? What if the universe isn't smooth at all, but is instead made up of tiny, discrete packets of information, like pixels on a cosmic screen? And what if the thing doing the pixelating isn't some abstract mathematical construct, but light itself, the very thing that allows you to see, read these words, and perceive the world around you? Here's something that will absolutely shatter your understanding of reality. Right now, as you're watching this video, photons are hitting your eyes in discrete chunks, not as a continuous stream. You think you're seeing a smooth video, but you're actually experiencing reality frame by frame, pixel by pixel, moment by moment. The universe might not just look pixelated, it might actually be pixelated at the most fundamental level. And the key to understanding this cosmic pixelation isn't hidden in some distant galaxy or locked away in a particle accelerator. It's in the light that's illuminating your room right now. In December 1900, a German physicist named Max Planck made a discovery that would eventually lead us to question the very fabric of reality itself. He found that energy doesn't flow continuously like water from a tappet comes in discrete packets, which he called quanta. This wasn't just a minor technical detail. This was the universe telling us, I don't do smooth, I do digital. And light was the first place we discovered this truth. But here's where it gets truly mind-bending. If light, the fastest thing in the universe, the thing that defines causality itself, is pixelated, then what does that say about space and time? If the messenger is digital, could the message itself be digital too? Before we go any further, I need you to do something for me. Hit that like button right now and subscribe if you haven't already, because over the next 3.5 hours, we're going to completely rebuild your understanding of reality from the ground up. And I want to know, drop a comment right now, telling me what country you're watching from and what time it is where you are. Because by the end of this video, you'll understand why the answer to that question is far stranger than you think. The speed of light might be constant, but time definitely isn't. And your location in spacetime matters more than you realize. Now, let's start with something simple. Let's talk about what light actually is, and why the answer to that question broke physics not once, but twice. For most of human history, we thought light was simple. You open your eyes, light comes in, you see stuff. Done. But here's the problem. Light refuses to behave like anything else in the universe. Is it a wave? Is it a particle? The answer is somehow both, neither, and something entirely beyond our comprehension. Let's go back to 1801. A British polymath named Thomas Young performed an experiment so simple a child could do it, yet so profound it would haunt physicists for the next 2 centuries. He took a light source, shone it through 2 narrow slits, and observed the pattern on a screen behind them. What he saw changed everything. If light were made of particles, tiny bullets of energy flying through space, you'd expect to see 2 bright lines on the screen, one behind each slit. That's just common sense, right? But that's not what happened. Instead, Young saw an interference pattern alternating bands of light and dark, exactly like what you'd see if you dropped 2 stones in a pond and watched the ripples overlap. This could only mean one thing. Light was a wave. The wave from one slit was interfering with the wave from the other slit, creating areas where the waves amplified each other, bright bands, and areas where they canceled each other out, dark bands. Case closed. Light is a wave. Physics could move on. Except it couldn't, because in 1905, a 26-year-old patent clerk named Albert Einstein published a paper that would win him the Nobel Prize and utterly shatter the wave theory of light. He was studying something called the photoelectric effect, the phenomenon where light hitting a metal surface knocks electrons loose. And here's what broke everything. The brightness of the light didn't matter for dislodging electrons. Only the color did. Think about that for a second. If light were a wave, Brighter light should mean more energy, which should knock electrons loose more easily. But that's not what happened. Dim blue light knocked electrons loose. Bright red light did nothing. It was like the electrons were saying, "I don't care how loud you shout. I only respond to a specific pitch." Einstein's explanation was revolutionary. Light doesn't come in continuous waves. It comes in discrete packets of energy called photons. The energy of each photon depends on its frequency, its color, not its intensity, its brightness. Red light has low-energy photons. Blue light has high-energy photons. An electron needs a minimum energy to break free, so it doesn't matter how many low-energy red photons you throw at it, none of them will work. But a single high-energy blue photon can do the job. So which is it? Is light a wave or a particle? Here's what will blow your mind. It's both. It's neither. It's something our brains literally aren't equipped to understand because we evolved in a world where things are either waves or particles, never both. This is called wave-particle duality, and it's not just true for light, it's true for everything in the universe. Electrons do it. Atoms do it. There's even evidence that molecules containing hundreds of atoms do it. The universe is fundamentally weirder than our everyday experience suggests. But here's where the pixelation comes in. When you measure light, when you actually detect it with your eyes or a camera or any instrument, it always arrives as a discrete particle, a photon. Never half a photon, never 1.5 photons. Always whole number integers. The universe, at its most fundamental level, deals in whole numbers. It's digital, not analog. Think of it like this. Imagine you're looking at a completely smooth gradient on your computer screen, going from pure black to pure white. It looks continuous, right? But zoom in far enough, and you'll see individual pixels, each one displaying a specific discrete color value. This smoothness was an illusion created by having so many tiny discrete elements that your eye can't distinguish them individually. That's what light is doing. That's what reality is doing. And this brings us to Max Planck, the man who started this whole revolution. In 1900, Planck was trying to solve a seemingly boring technical problem. Why do hot objects glow the color they do? Why does heated iron go from red to orange, to yellow, to white as it gets hotter? The classical physics of his day predicted something absurd, that hot objects should emit infinite energy in ultraviolet light. This was called the ultraviolet catastrophe, and it was a clear sign that something was deeply wrong with our understanding of nature. Planck's solution was desperate. He later called it an act of desperation because he couldn't see any other way forward. He proposed that energy doesn't flow continuously. It comes in minimum chunks, quantum packets. The size of these packets is determined by a fundamental constant of nature, now called Planck's constant, represented by the letter h. Its value is approximately 6.626 times 10 joule seconds. That number might not mean much to you, but here's why it's profound. It sets the minimum resolution of reality. Just like you can't have half a pixel on your screen, you can't have half a quantum of energy. The universe has a minimum size for certain properties. It's pixelated. When Planck first proposed this, even he didn't believe it was real. He thought it was just a mathematical trick, a convenient fiction that happened to match the experimental data. But over the next few decades, as quantum mechanics developed, physicists realized something terrifying. Planck's constant isn't just a mathematical convenience. It's describing something fundamental about the nature of reality itself. Now here's something that should make you pause. The reason you can see anything at all is because of this quantization. When electrons and atoms absorb energy, they don't gradually slide from one energy level to another like a car accelerating smoothly. They quantum jump, they teleport instantaneously from one discrete energy level to another. When they jump down to a lower energy level, they emit the excess energy as a photon of light. The color of that photon is determined by the size of the energy gap the electron jumped across. Every color you've ever seen, every rainbow, every sunset, every star in the night sky, all of it is the result of electrons making quantum jumps and spitting out photons of specific, discrete energies. The universe isn't painting with a continuous palette. It's working with a fixed set of crayons, and those crayons are determined by the quantum nature of reality. But if light is pixelated, what about space itself? What about time? Are they continuous, or are they pixelated too? And here's where things get truly strange, because the answer might depend on light itself. In 1905, the same year Einstein explained the photoelectric effect, he published another paper that would change everything, his special theory of relativity. And at the heart of relativity is a simple but profound statement. The speed of light is constant for all observers, regardless of their motion. This seems innocent enough until you realize what it actually means. If you're standing still and you measure the speed of a light beam, you'll get about 299,792,458 meters per second. Now imagine you're in a spaceship, traveling at half the speed of light in the same direction as that light beam. Common sense says you should measure the light going slower, right? You're chasing it, so relative to you, it should be moving at only half its normal speed. But that's not what happens. You still measure it going at 299,792,458 meters per second. Exactly the same speed. How is this possible? The answer is almost obscene in its implications. Space and time themselves must be flexible. They must warp and stretch to ensure that light always travels at the same speed relative to every observer. This means that as you approach the speed of light, time slows down for you, and distances contract in the direction of your motion. These aren't optical illusions or measurement errors. Time literally runs slower for you. Distances literally shrink. And the reason is light. The constancy of light's speed forces space and time to be relative, not absolute. But here's what most people miss. Einstein's relativity treats space and time as continuous. In his equations, you can divide space and time into infinitely small pieces. There's no minimum length, no minimum duration. But quantum mechanics, with its discrete energy levels and photons, suggests that reality is fundamentally discrete, not continuous. So which is it? This tension between the continuous nature of relativity and the discrete nature of quantum mechanics is one of the biggest unsolved problems in physics. And many physicists believe the resolution will involve discovering that space and time themselves are pixelated at incredibly tiny scales. The pixels would be so small that we can't currently detect them, but they'd be there, setting a fundamental resolution limit on reality itself. How small would these pixels be? Here's where we need to talk about something called the Planck length. In 1899, before even his quantum revolution, Max Planck realized you could combine fundamental constants of nature, the speed of light, the gravitational constant, and his own Planck's constant to create natural units of measurement. The Planck length comes out to about 1.6 times 10 meters. To put that in perspective, if an atom were the size of Earth, the Planck length would be about the size of a large molecule. It's incomprehensibly small. But many physicists believe this might be the pixel size of spacetime itself. Below this scale, our current theories of physics break down completely. The smooth fabric of spacetime that Einstein described might dissolve into some kind of discrete, foamy, quantum structure. And here's the truly mind-blowing part. Light itself might be the thing that enforces this pixelation. Let me explain why. When you try to probe smaller and smaller distances, you need higher and higher energy photons. This is because of a fundamental relationship discovered by Louis de Broglie in 1924. Every particle has a wavelength inversely proportional to its momentum. Higher energy means shorter wavelength, means you can see smaller details. This is why electron microscopes can see smaller things than optical microscopes. Electrons can have much shorter wavelengths than visible light photons. But here's the catch. If you try to create a photon with a wavelength smaller than the Planck length, it would require so much energy that it would create a black hole. The very act of trying to measure something smaller than the Planck length would collapse the region of space you're trying to measure. It's not just that we can't measure below the Planck length with current technology. The universe itself might prevent any possible measurement below this scale. Light, the thing we use to measure distances, might enforce a fundamental pixel size on spacetime. This is where physics starts to feel less like science and more like a cosmic joke. We use light to measure things. But light, by its very nature, might prevent us from measuring the smallest scales of reality. It's like trying to measure the thickness of a credit card with a ruler that's made of credit cards. The measurement tool itself becomes the limiting factor. And this connects to something profound about information. In 1948, Claude Shannon developed information theory, showing mathematically what it means for something to contain information. And here's the key insight. Information is fundamentally discrete. You can't have half a bit of information. Information comes in minimum chunks. If the universe is pixelated, if space-time itself has a minimum resolution, then the universe has a finite information content. Every region of space, no matter how large, can only contain a finite amount of information. This has led some physicists to propose that the universe isn't just like a computer simulation. It might literally be a computational process, with physical laws as the algorithm and quantum states as the data. But before you think this is just wild speculation, let me tell you about some actual experiments that have searched for evidence of space-time pixelation. Because this isn't just philosophy scientists are actively trying to detect whether the universe is pixelated. In 2015, researchers at Fermilab in Illinois built something called the holometer. This device uses lasers to search for quantum jitters in space-time itself. The idea is simple. If space-time is pixelated at the Planck scale, then precise measurements should reveal tiny random fluctuations, like the way a TV screen flickers if you look close enough. The holometer didn't find anything, which actually tells us something important. If space-time is pixelated, the pixels are smaller than what this experiment could detect. But the search continues. Gamma-ray telescopes are looking at light from distant cosmic explosions to see if high-energy and low-energy photons arrive at slightly different times. If space is pixelated, photons might interact slightly differently with space-time's grain, causing energy-dependent delays. So far, no definitive detection, but the searches are getting more sensitive every year. Here's what you need to understand. We're living through a revolutionary moment in physics. For the first time in history, we have the technology to potentially test whether reality itself is fundamentally continuous or discrete. We're not just philosophizing about pixels in the universe. We're building experiments to find them. And this brings us to something absolutely crucial. If the universe is pixelated, what's doing the pixelating? Is it just a property of space-time, or is there something deeper? Many physicists believe light itself, or more precisely, the quantum field that gives rise to photons, might be the thing that enforces the discrete nature of reality. Every point in space is filled with quantum fields. The electromagnetic field, which gives rise to photons, permeates all of space. Even in a perfect vacuum, with no particles present, these fields are there, constantly fluctuating at the quantum level. And these fluctuations are discrete, not continuous. The vacuum itself is seething with quantum activity virtual photons, constantly popping in and out of existence, living for impossibly brief moments before annihilating. This isn't speculation. These vacuum fluctuations have measurable effects. They cause something called the Casimir effect, where two metal plates placed very close together in a vacuum experience an attractive force because the quantum fluctuations between the plates are restricted compared to the fluctuations outside. This was predicted in 1948 by Dutch physicist Hendrik Casimir and experimentally confirmed in 1997. The vacuum isn't empty. It's pixelated with quantum activity. Now think about what this means. Light isn't just something that travels through space. Light, or rather, The electromagnetic field is part of the structure of space itself. And that structure is fundamentally discrete, fundamentally quantized, fundamentally pixelated. Light isn't just revealing the pixels of the universe. Light is the pixels of the universe, or at least one aspect of them. Are you starting to see why this question, is the universe pixelated by light, is so much deeper than it first appeared? We're not just asking whether light comes in discrete packets. We're asking whether light, by its very nature, enforces a discrete structure on reality itself. We're asking whether the thing that allows you to see is the same thing that determines the fundamental resolution of existence. Before we go deeper, I want to know, has your mind been blown yet? Drop a comment and let me know what's the most surprising thing you've learned so far. And if you're enjoying this deep dive, make sure you're subscribed, because we're just getting started. We've laid the foundation. Now we're going to build something truly extraordinary on top of it. Let's talk about something that will completely change how you think about seeing. When you look at something, let's say the screen you're watching this on, you think you're seeing it continuously, right? But you're not. Your eyes are being hit by photons one at a time, and each photon is making a discrete interaction with molecules in your retina. You're not watching a movie. You're watching a slideshow projected so fast that it creates the illusion of continuity. But here's where it gets weird. Your eye can actually detect single photons. In 2016, a team led by Rebecca Holmes at the University of Illinois demonstrated that human vision is sensitive enough to register individual photons hitting the retina. The experiment involved flashing incredibly dim light at subjects and asking them whether they saw it. Statistically, the results showed that people could detect flashes containing just a single photon. Think about that. Your vision is literally quantum limited. The minimum unit of light, one photon, is enough to trigger a signal in your visual system. You are a quantum detector. You are directly experiencing the pixelation of light every moment of every day, but your brain smooths it all out to create the illusion of continuous vision. And this connects to something profound about consciousness itself. Your subjective experience of the world is constructed by your brain from discrete inputs. Every photon is a bit of information. Your retina contains about 100 million photoreceptor cells, and each one is constantly being hit by photons, converting light into electrical signals. Your brain receives this torrent of discrete inputs and weaves them into the seamless, continuous experience you call vision. But your brain doesn't just passively receive this information. It actively predicts what it expects to see, and only updates its predictions when the incoming photon data contradicts them. In a very real sense, you're not seeing the world as it is. You're seeing a predictive model that your brain constructs, updated by discrete packets of information arriving in the form of photons. This raises a philosophical question that's starting to blur into a scientific one. Is your conscious experience of reality fundamentally continuous or discrete? When you watch a video like this one, you think you're experiencing a smooth flow of images and sounds, but you're not. The video itself is digital discrete frames played at a specific rate. The photons carrying that information to your eyes are discrete. The neural signals in your brain are discrete spikes of electrical activity. The continuity is an illusion constructed at multiple levels. So where does the continuity come from? Is it real, or is it just an artifact of having so many discrete events happening so quickly that you can't distinguish them? And here's an even stranger thought. If the universe itself is pixelated at the Planck scale, then everything, not just your perception, but reality itself, might be fundamentally discrete, with continuity emerging only as an approximation at larger scales. This is similar to how matter appears, solid even though it's mostly empty space. Your hand feels solid, but it's actually made of atoms, which are mostly empty space with tiny nuclei and electron clouds. The solidity is an emergent property, appearing only at macroscopic scales. Could continuity be the same? Could the smooth flow of time, the smooth fabric of space, be emergent properties that break down when you zoom in far enough? Now let's talk about something that combines quantum mechanics, relativity, and information theory into one of the most mind-bending concepts in modern physics, the holographic principle. This idea suggests that the universe might not just be pixelated, it might be a hologram, with all of reality encoded on a distant two-dimensional surface. In 1995, physicist Leonard Susskind proposed something radical. All the information contained in a volume of space can be encoded on the boundary of that volume, like a hologram. This came out of studying black holes, which we'll get to in a moment, but the implications are staggering. If the holographic principle is correct, the three-dimensional world you experience might be a projection from information encoded on a two-dimensional surface. Think of it like this. A hologram on a credit card is a two-dimensional pattern of light and dark regions, but when you shine light on it, it projects a three-dimensional image. The holographic principle suggests the universe works the same way. Everything in our 3D universe, including you, might be a projection from information encoded on a distant 2D surface. And here's where light comes back in. Holograms work because of the wave nature of light. The interference patterns created when light waves overlap encode three-dimensional information in a two-dimensional medium. If the universe is holographic, then light, with its wave-particle duality, its quantum nature, its fundamental role in spacetime, might be the mechanism by which information on a 2D boundary creates our 3D reality. The holographic principle isn't just wild speculation. It's a serious proposal that helps resolve paradoxes in black hole physics, and it's central to string theory, one of the leading candidates for a theory of quantum gravity. But what does it mean for pixelation? If information is encoded on a 2D surface and then projected to create 3D space, there's a maximum amount of information that can be contained in any region. That maximum is set by the surface area of the region's boundary, measured in Planck areas, the Planck length squared. This is called the Bekenstein bound, named after physicist Jacob Bekenstein, who worked it out in the 1970s. What this means is that every region of space has a finite information capacity, like a hard drive with a maximum storage size. And if information is finite and discrete, then the region itself must be discrete at some level. Space must be pixelated, with each pixel capable of storing a finite amount of information. Let me give you some numbers to make this concrete. For a region the size of a cubic meter, the Bekenstein bound says it can contain at most about 10 bits of information. That's a 1 followed by 69 zeros. That seems like a lot, but it's finite. You couldn't have an infinite amount of detail inside that cubic meter. There's a resolution limit. Now scale this up to the observable universe, which is about 46 billion light years in radius. The total information content of the observable universe, according to the holographic principle, would be encoded on its boundary and would be roughly 10 bits. Again, that's an incomprehensibly large number, but it's finite. The universe has a maximum information capacity. And here's what really scrambles your brain. If the universe has finite information content, then in principle, it could be simulated by a sufficiently large computer. Not a computer that exists in our universe. There isn't enough matter to build it. But a computer existing in a parent universe with different physics might be able to simulate our entire universe, including you, including your thoughts, including this very moment. Are we living in a simulation? I'm not going to give you a definitive answer, because nobody can. But here's what we can say. If the universe is pixelated, if it has finite information content, if the laws of physics are computational rules processing quantum information, then the simulation hypothesis isn't just science fiction. It's a legitimate scientific question that we might someday be able to test. Some physicists have proposed looking for glitches places where the pixelation of spacetime becomes visible, like when a video game renders something incorrectly. Others suggest looking for computational efficiency shortcuts, like how a computer game only renders what the player is looking at. If we're in a simulation, the simulator might only fully render things when they're being observed. which sounds suspiciously like quantum mechanics, where particles don't have definite properties until they're measured. I'm not saying we definitely live in a simulation. I'm saying that the question is now within the realm of science, not just philosophy. And the reason it's within the realm of science is because we've discovered that reality is fundamentally discrete, fundamentally quantized, fundamentally pixelated. And light, with its quantum nature and its central role in spacetime, might be both the messenger and the message, both the thing revealing the pixels and the thing creating them. Now, let's get back to black holes, because this is where the pixelation of the universe becomes impossible to ignore. Black holes are regions of spacetime where gravity is so strong that not even light can escape. And studying what happens to information when it falls into a black hole has led to some of the deepest insights about the quantized nature of reality. In 1974, Stephen Hawking discovered something shocking. Black holes aren't perfectly black. They emit radiation. This Hawking radiation comes from quantum effects right at the event horizon, the boundary of the black hole. Virtual particle pairs constantly pop into existence in the vacuum due to quantum fluctuations. Normally, they immediately annihilate each other. But at the event horizon, one particle can fall into the black hole while the other escapes, creating the appearance that the black hole is emitting radiation. Here's the crucial part. This radiation has a temperature, and that temperature is inversely proportional to the black hole's mass. Small black holes are hot. Large black holes are cold. And as a black hole emits radiation, it loses mass, which makes it hotter, which makes it radiate faster, which makes it lose mass faster, in a runaway process that eventually causes the black hole to evaporate completely. When Hawking first proposed this, it created a paradox that still hasn't been fully resolved. If a black hole can evaporate completely, what happens to the information that fell into it? Quantum mechanics says information can't be destroyed. This is called unitarity. But if a black hole evaporates into Hawking radiation, which is essentially random thermal radiation, the information seems to be lost. This black hole information paradox has driven much of theoretical physics for the past 50 years. And the leading solutions all involve the idea that information is somehow encoded on the black hole's event horizon in a discrete, pixelated form. Jacob Bekenstein proposed that black holes have entropy, a measure of disorder or information content, and that this entropy is proportional to the surface area of the event horizon, not the volume. Every Planck area on the horizon can store one bit of information. The event horizon is pixelated, with each pixel being one Planck area in size. Think about what this means. When you fall into a black hole, all the information about you, every atom, every quantum state, everything that makes you gets scrambled and encoded on the black hole's surface as it crosses the event horizon. You're not inside the black hole. You're smeared across its surface as a pattern of information. And as the black hole evaporates, that information gets slowly released in the Hawking radiation. This is deeply weird. It means that in some sense, the interior of a black hole might not even exist. All the information is on the surface. The interior might be a kind of holographic projection from that surface. And this is one of the key pieces of evidence supporting the holographic principle for the entire universe. But here's where it connects back to light. Hawking radiation is light. Well, it's mostly photons, along with other particles, but fundamentally, it's electromagnetic radiation. And the temperature of this radiation is set by the pixelation of the event horizon. Each Planck area pixel on the horizon corresponds to a unit of entropy, and the total entropy determines the temperature, which determines the spectrum of emitted photons. Light is revealing the pixelation of black holes. Light is carrying away the information encoded on the horizon. Light is the messenger that tells us reality is discrete at the most extreme conditions we know of. And this has led to what might be the most important insight. The fundamental currency of the universe isn't matter or energy, it's information. And information is always discrete. you can't have half a bit. Physical systems don't store and process information continuously. They do it in discrete quantum states. A photon is a quantum bit-a-qubit of information. Its polarization can be horizontal or vertical, or any quantum superposition of both. When you measure it, you get 1 bit of information. Every photon carries information, and the universe is constantly processing this information according to the laws of physics. This is why some physicists, like John Wheeler, proposed the slogan "it from bit," the idea that every physical thing, every it, derives from information, from bits. Matter, energy, space-time, all of it might be emergent properties of an underlying information processing system. And light, as the fastest carrier of information in the universe, plays a central role in this cosmic computation. Now, I want you to think about something personal. Every time you look at something, a loved one's face, a sunset, these words on your screen, you're receiving information encoded in photons. Each photon is a quantum bit carrying data from the world to your eyes. Your entire visual experience of reality is a stream of discrete information packets hitting your retina at the quantum limit of detection. You are not separate from this pixelated universe. You are made of it. Every atom in your body is held together by electromagnetic forces carried by virtual photons, constantly being exchanged between charged particles. The electrons in your atoms are absorbing and emitting photons right now, jumping between discrete energy levels. Your DNA is being protected from damage by molecular machinery that uses light to detect and repair errors. And your brain, the thing, allowing you to understand these words processes information in discrete spikes of neural activity. Neurons fire or don't fire. The action potential is all or nothing. Your thoughts, your consciousness, your sense of self, all of it emerges from patterns of discrete neural firing, processing information that arrived from the outside world in the form of discrete photons. Are you feeling it yet? That sense that the ground is shifting beneath your feet? That the solid, continuous reality you took for granted is dissolving into something stranger and more wonderful? Good, because we're about to go even deeper. Let me ask you a question that sounds simple, but isn't. What is light? We've talked about photons, about waves, about quantum fields, but what is light really? Is it a thing, or is it an event? Is it a particle traveling through space, or is it an interaction between quantum fields? Here's what modern physics tells us. A photon isn't really a particle in the sense of a tiny billiard ball flying through space. It's better thought of as excitation in the electromagnetic field, a ripple, a quantum of energy propagating through the field. When we say a photon travels from point A to point B, what we really mean is that the electromagnetic field at point A transferred energy to the electromagnetic field at point B, and this transfer happened in a discrete quantum unit. But even this isn't quite right, because of something called quantum field theory. According to QFT, which is the most successful theory in all of physics, particles don't actually exist as distinct objects. What exists is quantum fields filling all of space, and what we call particles are just excited states of these fields. A photon is what happens when the electromagnetic field is in an excited state. Now here's where your brain really starts to hurt. In quantum field theory, when a photon travels from one place to another, it doesn't take a single path. It takes all possible paths simultaneously. This is Feynman's path integral formulation, developed by Richard Feynman in the 1940s. To calculate the probability of a photon going from A to B, you have to sum up the contributions from every possible path. It could take straight lines, curves, loops, even paths that go backward in time and then forward again. The reason we see photons traveling in straight lines is because the contributions from the weird paths mostly cancel out through quantum interference, leaving only the straight path with significant probability. But the other paths are still there in the mathematics, and they have measurable effects. This is why light bends around obstacles in diffraction patterns. The straight line path isn't the only one contributing. So a photon isn't a particle following a path. It's a probability amplitude spread across all possible paths, collapsing into a discrete event when it interacts with something. Light isn't a thing, it's a process, an interaction, a transfer of information between quantum fields. And here's the truly mind-bending implication. If photons don't take definite paths until they're measured, and if they're constantly being emitted and absorbed by every charged particle in the universe, then the whole universe is connected by a vast web of potential photon exchanges. Every point in space is potentially connected to every other point by photons that could be exchanged. And these potential connections are what create the structure of spacetime itself. This is the picture you get from quantum field theory. Spacetime isn't a stage where things happen. Spacetime is the pattern of relationships between quantum fields, and those relationships are mediated by particle exchanges. Photons aren't just moving through space-time, photons are creating space-time by defining which points can causally influence each other. And because photons are discrete, these connections are discrete. Space-time, at the quantum level, might not be smooth at all. It might be more like a network, with nodes representing events and links representing possible particle exchanges. This is the idea behind something called quantum gravity, proposed by Fotini Markopoulou and others, the notion that spacetime emerges from a quantum network of discrete connections. If this is true, and it's still highly speculative, then the universe isn't just pixelated. It's more like a graph, with vertices and edges, and what we perceive as continuous spacetime is an emergent approximation that works at large scales. At the Planck scale, spacetime would dissolve into something discrete, combinatorial, fundamentally different from our everyday experience. And light would be the thing revealing this structure, because light defines causality. The speed of light is the maximum speed at which information can travel, which means it's the maximum speed at which cause and effect can propagate. Two events can only influence each other if a light signal could travel between them. Light defines the causal structure of spacetime. So is the universe pixelated by light? In a very real sense, yes. Light, or more precisely, the quantum electromagnetic field, is one of the fundamental fields that structure reality. Its quantum discrete nature might enforce discreteness on spacetime itself, and its role in defining causality might mean that the network of possible photon exchanges literally creates the geometry of spacetime. Let me give you something concrete to think about. Right now, photons from distant stars are hitting your location on Earth. Some of these stars are thousands of light years away, which means the photons have been traveling through space for thousands of years. But here's the weird part. From the photon's perspective, no time has passed at all. Special relativity tells us that as you approach the speed of light, time dilation becomes extreme. At exactly the speed of light, time stops completely. A photon doesn't experience time. From its perspective, if it could have a perspective, it's emitted and absorbed in the same instant, even if that takes billions of years from our perspective. This means that photons connect different points in spacetime with zero proper time between them. They create light-like connections, null geodesics, that link distant events without any time passing from the photon's point of view. The entire history of the universe, from the photon's perspective, is instantaneous. Now think about what this means for the structure of reality. If photons don't experience time, and if photons are constantly being exchanged between all charged particles, then in some sense, the entire universe is connected in a timeless web of photon exchanges. Past, present, and future are all linked together through light-like connections where no time passes. This is starting to sound more like a block universe, the idea that all of spacetime exists simultaneously, with past, present, and future all equally real in the flowing river of time we subjectively experience. And the thing connecting it all, the thing making it all simultaneous from its own perspective, is light. But here's where it gets personal again. You are part of this web. Every photon hitting your eye right now is creating a light-like connection between you and whatever emitted it. When you look at the sun, you're connecting to an event that happened 8 minutes ago through a photon that experienced 0 time during its journey. When you look at Andromeda Galaxy, you're connecting to an event that happened 2.5 million years ago. But again, from the photon's perspective, no time passed. Your conscious experience is assembled from these timeless connections. The information flowing into your brain right now came from events at many different times. The recent past from nearby objects, the distant past from faraway objects, but all of it arriving in the same instant, as far as the photons are concerned. Your present moment is actually a patchwork of many different pasts, stitched together by light. And because photons are discrete, this patchwork is fundamentally grainy. You're not receiving a continuous stream of information from the world. You're receiving discrete packets, quantum bits, arriving one at a time, or in bunches, creating the illusion of continuity, only because so many of them arrive so quickly. Now let's talk about something that will completely reframe everything we've discussed. The double-slit experiment, but with a twist you probably haven't heard about. We mentioned earlier that Thomas Young's double-slit experiment showed light behaving like a wave. But there's a modern version of this experiment that reveals something far stranger about the nature of reality. If you perform the double-slit experiment with photons sent one at a time, so there's only ever one photon in the apparatus at any moment, you'd think each photon would go through one slit or the other, like a particle should. But that's not what happens. Even when sent one at a time, the photons build up an interference pattern over time. Each individual photon somehow knows about both slits. This is quantum superposition in action. The photon isn't going through one slit or the other. It's going through both slits simultaneously, in a quantum superposition, and interfering with itself. Only when you detect which slit it went through does it collapse into going through one slit or the other. And when you do that, the interference pattern disappears. But here's the twist. In 1978, physicist John Wheeler proposed a delayed choice experiment. You let the photon enter the apparatus without deciding whether to measure which slit it went through or to look for interference. Only after the photon has already passed through the slits do you make the choice. If you choose to measure which slit, you find it went through one slit. If you choose to look for interference, you see interference as if it went through both. This experiment has been performed, and the results confirm Wheeler's prediction. Your choice of what to measure, made after the photon has passed through the slits, retroactively determines whether it went through one slit or both. The future is affecting the past, or more accurately, what we call past and future aren't as separate as we think. In 2007, French physicist Alain Aspect and colleagues performed an even more mind-bending version, using satellite signals and photons that had been traveling for millions of years from distant quasars. The choice of measurement affected the behavior of photons that had been traveling since long before the experiment was designed. What does this tell us? It tells us that photons, and by extension, all quantum particles, don't have definite properties until they're measured. They exist in superpositions, taking all possible paths, being in all possible states, until an interaction forces them to choose one definite state. And these interactions can be separated by vast distances and times. This is called quantum non-locality, and it's been experimentally confirmed in numerous ways. Two photons can be entangled so that measuring one instantly affects the other, even if they're on opposite sides of the galaxy. Einstein called this spooky action at a distance and didn't like it, but experiments by Alain Aspect in 1982 and many others since have confirmed it's real. Now, what does entanglement have to do with pixelation? Everything. Because entanglement reveals that the fundamental units of reality aren't individual particles, they're quantum states that can be spread across space. When two photons are entangled, they don't have individual, separate states. They share a single quantum state that extends across space. This means that the pixels of reality aren't localized at points in space. They're non-local. A single pixel, a single quantum of information, can be spread across vast distances. The universe isn't pixelated in the way a TV screen is, with each pixel sitting at a specific location. It's pixelated in a much stranger way, where the pixels can be quantum superpositions spread across space and even time. Think of it like this. Imagine you have a photograph, but instead of each pixel having a definite color at a definite location, the pixels are entangled with each other. The color of one pixel depends on the color of distant pixels in a way that can't be described by any local hidden variables. You can't say, this pixel is red, without also specifying the quantum state of other pixels it's entangled with. The photograph is fundamentally non-local. That's what reality is like. The universe is a cosmic quantum state where everything is potentially entangled with everything else. The individual pixels, the quanta of energy, the quantum bits of information, aren't independent. They're correlated in ways that transcend space and time. And light, again, plays a central role. Photons are the easiest particles to entangle and maintain in an entanglement over long distances. This is why quantum communication and quantum computing experiments use photons. They're perfect carriers of quantum information because they don't interact strongly with their environment, so their quantum states remain coherent over long distances. Every photon hitting your eye right now is carrying quantum information. Some of those photons might be entangled with photons that went somewhere else, creating non-local correlations between you and distant parts of the universe. You are quantum mechanically entangled with the cosmos. Now, let me hit you with something that ties all of this together: the observer effect. In quantum mechanics, the act of observation isn't passive. You can't measure something without affecting it. And for photons, the effect is extreme. When you detect a photon, you destroy it. The photon is absorbed by whatever detector you use, and it ceases to exist. This means that every time you see something, you're destroying the photons that carried the information to you. Vision is fundamentally destructive. You can't see light without absorbing it, and you can't absorb it without collapsing its quantum state. This raises a profound question. Does reality exist when no one is looking at it? If photons don't have definite properties until they're measured, and if measuring them destroys them, then what is the status of the electromagnetic field when it's not being observed? The mainstream interpretation is that the field exists in a quantum superposition of all possible configurations, and only collapses into a definite state when an interaction happens. But what counts as an interaction? Does it require a conscious observer? Or is any physical interaction sufficient? Most physicists believe consciousness isn't special any interaction that creates entanglement with the environment is sufficient to cause decoherence and effective collapse. But there's a minority view, championed by physicists like John von Neumann and Eugene Wigner, that consciousness plays a fundamental role in collapsing the quantum wave function. I'm not going to tell you which interpretation is correct, because nobody knows. But I want you to appreciate how deep the rabbit hole goes. The pixels of reality, the individual quanta of light, might not have definite properties until they interact with something. And you, by seeing, are causing those interactions. You are collapsing wave functions with every glance. You are playing an active role in creating the definite, pixelated reality you experience. This isn't mysticism. This is quantum mechanics taken seriously. The universe is participatory. Observer and observed aren't separate. They're entangled. You affect what you see by seeing it. And what you see is fundamentally discrete, fundamentally quantized, fundamentally pixelated. Before we continue, I want you to pause and reflect on something. How are you feeling right now? Is your sense of reality shifting? Are you seeing the world differently? Drop a comment and let me know what's going through your mind. And if this is blowing your mind as much as I hope it is, Please share this video with someone who you think would appreciate having their reality shattered and rebuilt. Now, let's talk about something that will connect the pixelation of the universe to the origin of everything, the cosmic microwave background. This is light photons that has been traveling through space for over 13 billion years, since just 380,000 years after the Big Bang. And studying these ancient photons has revealed the pixelation of the universe in ways that are both beautiful and profound. In the early universe, everything was hot and dense, so hot that atoms couldn't form. Electrons and protons existed as a plasma, and photons were constantly being absorbed and re-emitted, scattering off the charged particles. This made the universe opaque to light, like being inside a glowing fog. But as the universe expanded and cooled, it reached a critical temperature, about 3000 Kelvin, where electrons and protons could combine to form neutral hydrogen atoms. This is called recombination. Suddenly, photons could travel freely without constantly scattering. The universe became transparent, and those photons have been traveling through space ever since, cooling and redshifting as the universe expands. Today, we detect those photons as microwave radiation, the cosmic microwave background, or CMB. And here's what's extraordinary. The CMB shows us what the universe looked like at recombination. It's a baby picture of the cosmos, taken when the universe was just 380,000 years old. And this picture is pixelated, not because of any limitation in our detectors, but because the universe itself was pixelated. The CMB shows tiny temperature fluctuations, regions slightly hotter or colder than average, and these fluctuations are the seeds of all structure in the universe. The regions that were slightly denser became the first stars, galaxies, and galaxy clusters. But here's what matters for our discussion. These fluctuations are quantum in origin. They come from quantum fluctuations in the early universe that got stretched to cosmic scales during inflation, a period of exponential expansion that happened in the first fraction of a second after the Big Bang. Quantum mechanics predicts that even empty space has fluctuations, virtual particles popping in and out of existence. Normally, these fluctuations are incredibly tiny at the Planck scale, but during inflation, these quantum fluctuations got amplified to enormous scales, becoming the density fluctuations we see in the CMB. This means that the large-scale structure of the universe, the distribution of galaxies, the cosmic web of filaments and voids, all originated from quantum fluctuations. The discrete, pixelated nature of quantum mechanics at the smallest scales got imprinted on the cosmos at the largest scales. And the messenger bringing us this information is light photons from the CMB that have traveled for billions of years to reach us. These photons are showing us the pixelation of the early universe frozen in time. But there's another form of pixelation in the CMB that's even more fundamental. The photons themselves are discrete. The CMB isn't a continuous field. It's a bath of photons, each one carrying a discrete quantum of energy. When we map the CMB, we're counting individual photons arriving from different directions, and from their energies and distribution, we're reconstructing the state of the early universe. Modern CMB experiments, like the Planck satellite, have mapped these fluctuations with incredible precision. And here's what they've found. The fluctuations match exactly what quantum mechanics predicts. The statistics of the hot and cold spots in the CMB follow a quantum pattern. The universe is confirming, through light from its own infancy, that it is fundamentally quantum, fundamentally discrete. Now let me tell you about something even more spectacular. We can use the CMB to measure the pixelation of space itself. If space is fundamentally discrete at the Planck scale, this should leave an imprint on the CMB. Specifically, it should create a cutoff, a maximum frequency for the fluctuations, because you can't have fluctuations smaller than the pixels of space. Some theories of quantum gravity predict this cutoff should be visible in the CMB. So far, we haven't seen it, which tells us that if space is pixelated, the pixels are smaller than we can currently measure. But future CMB experiments might detect this cutoff, finally confirming that space itself is fundamentally discrete. And this connects to something profound. The universe has a maximum temperature. It's called the Planck temperature, and it's about 1.4 times 10 Kelvin. Above this temperature, thermal fluctuations become so energetic that they create microscopic black holes. The concept of temperature breaks down. You can't make something hotter than the Planck temperature. The universe, at the moment of the Big Bang, was at or near this maximum temperature. And as it expanded and cooled, it passed through discrete temperature thresholds where different physics became relevant. First, the strong force separated from the other forces. Then the electromagnetic and weak forces separated, and quarks combined into protons and neutrons. Then nuclei formed. Then atoms formed. Each transition happened at a specific temperature, a specific time after the Big Bang. The history of the universe is fundamentally discrete, a series of phase transitions, each one qualitatively changing the nature of reality. And we know about these transitions because of light. The photons in the CMB carry information about the last major transition recombination. The photons from the first stars carry information about reionization, when the first stars formed and reionized the hydrogen gas in the universe. Light is our archaeologist, revealing the discrete stages in the universe's evolution. And every photon we detect is a piece of the puzzle, a pixel in the cosmic picture. Now I want to talk about something that connects quantum mechanics, information theory, and thermodynamics in a way that reveals deep truths about the pixelated nature of reality, Landauer's principle. This principle, proposed by Rolf Landauer in 1961, says that erasing information has a thermodynamic cost. Specifically, erasing one bit of information requires dissipating at least kT lane. 2 energy is heat, where K is Boltzmann's constant and T is temperature. This might sound technical, but it has profound implications. It means that information is physical. You can't separate information from physics. Every bit of information corresponds to a physical state, and changing that state requires energy. Now think about what this means for the universe. If the universe has finite information content, as the holographic principle suggests, then the universe has a maximum entropy, a maximum amount of disorder or information it can contain. And as the universe evolves, it's constantly processing information quantum states, evolving according to the laws of physics. Every physical process is an information process. Every interaction between particles is an exchange of information. Every measurement is an extraction of information. And all of this happens in discrete quantum steps. Light plays a central role in this cosmic information processing. Photons carry information faster and more efficiently than any other particle. When an electron jumps between energy levels in an atom, it emits or absorbs a photon, changing the information content of the system. When you see something, photons carry information from the object to your eye. When scientists use light to probe matter, they're using photons to extract information about the system. And because photons are discrete, information transfer is discrete. You can't transfer half a photon's worth of information. Information flows in quantum bits, and light is the primary carrier of these qubits in the universe. This has led some physicists to propose that the universe is literally a quantum computer, processing information according to the laws of quantum mechanics. The total number of qubits is finite, set by the Bekenstein bound. The processing speed is limited by the Bremerman's limit, which says you can't perform more than 1.36 times 10 operations per second per joule of energy. If you calculate the maximum computational power of the observable universe, using its total mass energy and maximum possible processing speed, you get something like 10 operations on 10 bits. That's an incomprehensibly large computer, but it's finite. The universe has finite computational resources. And if that's true, then reality is fundamentally limited in resolution. There's a maximum amount of detail that can exist, a maximum rate at which things can change, a fundamental discreteness to all processes. The universe is pixelated not just in space, but in time, in state space, in every dimension of existence. Light, as the fastest carrier of information and the definer of causality, sets the pace for this cosmic computation. The speed of light isn't just a speed limit, it's the clock speed of the universe, determining how fast information can propagate and how fast the computation of reality can proceed. Now let me share something personal that connects all of this to your daily life. Every digital device you own, your phone, your computer, the screen you're watching this on, works because we've learned to manipulate the quantum properties of matter. The transistors in your computer chip are getting so small that quantum effects dominate their behavior. Modern processors have features just a few nanometers across small enough that quantum tunneling, where electrons spontaneously pass through barriers they shouldn't be able to cross, becomes a major problem. Your camera works by detecting individual photons hitting a sensor array. Each pixel in your camera's sensor can register single photons, converting light into electrical signals that get processed into the images you see. Photography is literally the art of counting and recording individual photons. And the internet itself? It works by sending information encoded in light pulses through fiber optic cables. Each bit of data is represented by the presence or absence of photons. The digital world is fundamentally built on manipulating discrete packets of light to carry discrete packets of information. You are living in a world shaped by our understanding that reality is pixelated. The entire digital revolution happened because we discovered quantum mechanics, because we learned that energy and information are discrete, because we figured out how to manipulate individual photons and electrons. And here's something that should give you chills. The device you're using to watch this video is manipulating reality at the quantum level billions of times per second. Every calculation your processor performs involves quantum mechanical processes. Every image on your screen is created by controlling the emission of individual photons from millions of tiny light sources. You are wielding quantum technology that would have seemed like magic to someone a century ago. But it's not magic. It's applied knowledge of how the universe actually works. It's taking seriously the fact that reality is discrete, quantized, pixelated. And as our technology advances, we're going to get better and better at exploiting this fundamental nature of reality. Quantum computers, which are just starting to become practical, will manipulate quantum superpositions and entanglement to perform calculations impossible for classical computers. They'll use individual photons and atoms as qubits, processing information in ways that leverage the strange, non-local, pixelated nature of quantum mechanics. Quantum cryptography, which is already being used for secure communications, uses the fact that you can't measure a quantum state without disturbing it. Send information encoded in photon polarizations, and any eavesdropper will inevitably leave traces, making perfectly secure communication possible. And future technologies we can barely imagine will exploit even more exotic quantum effects. Quantum teleportation, transferring quantum states from one location to another using entanglement, has already been demonstrated. Quantum sensors can detect gravitational waves, magnetic fields, and other phenomena with unprecedented sensitivity. We're learning to read and write the pixels of reality directly. This is the world you live in. This is the future you're moving toward. And it's all built on the foundation of a simple but profound truth. The universe is not continuous. It's discrete. It's pixelated. And light, beautiful, mysterious light is showing us how to read and write the code of reality itself. Now let's talk about time, because if space is pixelated, what about time? Is there a minimum duration? A chronon, the temporal equivalent of a pixel? This question takes us to some of the strangest territory in all of physics. Classical physics treats time as continuous. You can divide a second into milliseconds, microseconds, nanoseconds, and keep going forever with no minimum duration. But quantum mechanics suggests this can't be right. If energy is quantized, and if the Heisenberg uncertainty principle relates energy and time, then there should be a fundamental limit to how finely we can divide time. That limit is the Planck time, about 5.4 times 10 seconds. This is the time it would take light to travel 1 Planck length. Below this timescale, our current theories of physics break down. Space and time become quantum, and we need a theory of quantum gravity to describe what happens. Some theories of quantum gravity, like loop quantum gravity, explicitly propose that time is discrete. In these theories, time doesn't flow smoothly. It advances in tiny jumps, each jump being roughly 1 Planck time in duration. Reality isn't a movie playing at infinite frame rate. It's playing at about 10 frames per second. That's fast enough that we'd never notice the discreteness, but it's there. If this is true, it has mind-blowing implications. It means there's a fundamental limit to how fast things can change. No process can happen faster than 1 Planck time. The universe has a maximum frame rate. And light, once again, is central to this. The Planck time is defined using the speed of light. It's the time light takes to cross the Planck length. Light sets the temporal pixelation of reality just as it sets the spatial pixelation. But here's where it gets really weird. If time is discrete, then continuous motion is impossible. Nothing actually moves smoothly. Everything teleports from one position to the next, with each teleportation taking 1 Planck time. At large scales, with many tiny jumps, this looks like continuous motion, just like how a movie looks smooth even though it's really just a sequence of still frames. You right now, sitting or standing wherever you are, aren't continuously existing through time. You're being recreated frame by frame, about 10 times per second. Each frame is a complete quantum state of all the particles that make up your body and brain. Your consciousness, your thoughts, your sense of continuous existence, all of it emerges from this rapid succession of discrete states. This is similar to the Buddhist concept of momentariness, the idea that things don't persist through time, but are constantly coming into and going out of existence. Modern physics might be confirming ancient philosophical insights about the nature of time and existence. And here's something even stranger. Different observers might experience different temporal pixelation. Just as relativity tells us that different observers disagree about simultaneity, about which events happen at the same time, some theories suggest that different observers might experience different temporal resolutions. If you're moving at high speed relative to me, not only does your time run slower from my perspective, but the temporal pixelation, the size of the chronons, might be different. Time dilation isn't just time slowing down. It might be the pixels of time getting stretched. This is highly speculative, and we have no experimental evidence for it yet. But it's a logical consequence of combining quantum mechanics with relativity. And it suggests that the pixelation of reality isn't absolute. It depends on the observer's reference frame. Light, traveling at the speed of light, experiences no time at all. From a photon's perspective, there are no temporal pixels because there's no time. The entire history of the universe, from the photon's point of view, is a single instant. Beginning and end are simultaneous. This is why some physicists talk about the block universe, the idea that all of spacetime exists as a four-dimensional block, with past, present, and future all equally real. Our subjective experience of time flowing is an illusion created by how we, as observers embedded in the universe, process information. And that processing happens in discrete steps. Your neurons fire in discrete action potentials. Your retina responds to discrete photons. Your conscious experience is constructed from discrete moments of perception, stitched together by your brain to create the illusion of continuity. But here's what's profound. Even if time is an illusion, the information processing is real. The universe is really computing, really processing quantum information according to physical laws, and you are part of that computation. Your brain is a subsystem of the universal quantum computer, processing information about the rest of the universe. Every thought you have, every decision you make, every experience you undergo, all of it is information processing happening in the quantum states of neurons in your brain. And that information arrived, ultimately, from photons hitting your retinas and other sensory organs. Light is the primary information channel connecting you to the external world. So when you ask, is the universe pixelated by light? You're really asking, is the information structure of reality discrete? And does light play a fundamental role in that structure? The answer, increasingly, seems to be yes. Now, I want to share something that ties all of this together in a way that's both scientifically rigorous and deeply meaningful for how you understand your place in the cosmos. It's about the role of observation in creating reality. We've talked about how photons don't have definite properties until they're measured. We've talked about how quantum states exist in superposition until they interact with something. But what counts as a measurement? What counts as an observation? In the early days of quantum mechanics, some physicists thought consciousness was necessary to collapse the wave function. But most modern physicists believe that any interaction that creates entanglement with the environment is sufficient. This process is called decoherence. Here's how it works. When a quantum system interacts with its environment, which is constantly happening for any macroscopic object, different components of its quantum superposition become entangled with different states of the environment. These different components then evolve independently and can't interfere with each other anymore. The quantum behavior disappears, and the system behaves classically. Photons play a huge role in decoherence. Any object above absolute zero temperature emits thermal radiation photons. These photons carry away information about the object's state, creating entanglement between the object and the electromagnetic field. This is one of the main mechanisms by which quantum superpositions collapse in everyday life. So in a sense, light is constantly measuring everything, constantly collapsing superpositions, constantly creating classical reality from quantum possibility. The universe is continuously observing itself through the exchange of photons. But here's what's profound. You are part of this process. When you see something, photons that were emitted or reflected by that object enter your eye and create correlations between the object and your brain state. You become entangled with what you're observing. The distinction between observer and observed breaks down at the quantum level. This isn't just philosophy. It's experimentally testable. In quantum optics experiments, you can see how the act of detection changes the statistics of the photons being detected. You can't passively observe quantum systems. Observation is always an active process that changes what you are observing. And this connects to something deeper, the participatory universe. John Wheeler, one of the giants of 20th century physics, proposed that the universe doesn't exist in a definite state until it's observed. Quantum mechanics suggests that before observation, only probabilities exist. The definite, concrete reality we experience emerges through the process of observation. Wheeler even suggested that the past might not be definite until it's observed. His delayed choice experiment, which we discussed earlier, shows that measurements made now can affect what happened in the past. This doesn't mean you can change history in the sense of going back and killing your grandfather. It means that the past exists in a quantum superposition until it's measured. And our measurements now are part of the process that makes the past definite. This is incredibly strange, but it's what quantum mechanics seems to be telling us. And photons' light are the primary means by which we observe the universe, both the present and the past. When you look at the night sky, you're looking at the past. The light from distant stars was emitted years, centuries, even millennia ago. And by observing that light, you're participating in making that past definite. The universe is not a stage where things happen. The universe is a participatory process where observation and reality co-create each other. And light is the medium of that co-creation. Now, how does this make you feel? Do you feel more connected to the universe, knowing that you're not separate from it, that your observations are actively shaping reality? Or does it feel overwhelming, like the ground of reality has dissolved beneath your feet? Either reaction is valid. This is genuinely weird stuff, and it should make you uncomfortable, but it should also fill you with wonder. You're not a passive observer watching a predetermined show. You're an active participant in the cosmic process of reality creation. And here's something empowering. Understanding this gives you a new perspective on your life and choices. If reality is participatory, if your observations matter, then your attention matters. What you choose to pay attention to, how you choose to observe the world, affects your experience of reality. This isn't mysticism or wishful thinking. It's quantum mechanics taken seriously. The universe you experience is constructed by your brain from information carried by photons and other particles. By changing what you pay attention to, you literally change the information your brain uses to construct your reality. You can't change the external world just by thinking about it differently. That would be magical thinking. But you can change your experience of the world, which is the only world you'll ever know, by changing how you observe it. And in quantum mechanics, observation is not passive. Observation creates reality. So here's a practical application of all this physics. Pay attention to what brings you joy, what gives you meaning, what makes you feel connected to something larger than yourself. Your attention is limited. You can only process so much information. Choose wisely what you observe, because you're actively shaping your experienced reality with every photon that hits your retina, every quantum measurement your senses perform. Now let's talk about the future. Where is all of this going? What will we discover next about the pixelated nature of reality? Several major experiments are underway or planned that could revolutionize our understanding. Gravitational wave detectors, like LEGO and the future LISA space-based detector, might detect quantum effects in gravity, revealing whether spacetime itself is quantized. Next-generation particle colliders might find evidence of new physics at the Planck scale. Quantum computers might become powerful enough to simulate quantum field theories and test ideas about the computational nature of reality. But there's also a chance we'll hit fundamental limits. If reality is truly pixelated at the Planck scale, there might be things we can never know, measurements we can never make, questions we can never answer. The universe might have an intrinsic information horizon beyond which we can't see, not because of technological limitations, but because of the fundamental nature of reality itself. This would be both humbling and beautiful. Science wouldn't end. There would still be infinite complexity to explore within the boundaries of what's knowable. But we'd have to accept that the universe keeps some secrets, that reality has a privacy screen at the Planck scale that we can never peek behind. Or maybe we'll find a way around these limits. Maybe we'll discover that the Planck scale isn't fundamental, that there's deeper structure beneath it. Maybe we'll find that what we think of as spacetime is just an emergent approximation, and the true degrees of freedom of the universe are something entirely different. One radical possibility is that space and time themselves are emergent, that they're not fundamental, but arise from something more basic. Several approaches to quantum gravity, including string theory and loop quantum gravity, suggest this might be true. The fundamental reality might be a network of quantum information, with space and time emerging as useful approximations at large scales. If this is right, then asking whether space is pixelated is asking the wrong question. Space isn't pixelated. Space doesn't fundamentally exist. What exists is quantum information, and space is just how that information organizes itself at macroscopic scales. Light wouldn't be traveling through space-light, would be information propagating through the network. This is deeply weird, and we're far from confirming it. But it's where the math seems to be pointing. And if it's true, it would mean that everything we think of as physical matter, energy, space, time is actually informational. The universe is made of bits, and those bits are processing themselves according to mathematical rules we call physical laws. And you are a pattern in this cosmic information processing system. Your thoughts, your consciousness, your sense of self, all of it is a persistent pattern of information, maintaining itself through constant interaction with the rest of the universe. You're a wave in the ocean of cosmic information, made of the same stuff as the rest of reality, but organized in a special way that creates self-awareness. This brings us to perhaps the deepest question of all. Why is there something rather than nothing? If the universe is made of information, where did the information come from? Who or what set up the rules? Who or what started the computation? Nobody knows. This might be a question science can never answer. Or it might be that the question doesn't make sense, that the universe has always existed in some form, that it's somehow necessary, that asking why it exists is like asking what's north of the North Pole. But here's what we can say. The universe exists, and it's capable of giving rise to structures complex enough to ask questions about their own existence. You are the universe asking questions about itself. You are a way for the cosmos to know itself, to observe itself, to wonder at its own existence. And light photons bouncing around, carrying information, creating causal connections, enabling vision and observation is a central character in this cosmic story. Without light, there would be no vision. Without vision, complex life as we know it wouldn't exist. Without complex life, there would be no consciousness, no science, no questions about the nature of reality. Light is not just showing us that the universe is pixelated. Light is part of the mechanism by which the universe creates beings capable of noticing and understanding its own pixelation. Light is how the universe sees itself. Let me leave you with this. Every time you open your eyes, every time you look at the world around you, you're participating in one of the most profound processes in existence. Photons emitted from distant atoms, traveling at the cosmic speed limit, are arriving at your retina and creating information about the external world inside your brain. You're not separate from the universe, looking at it from outside. You're the universe looking at itself from inside. And that universe is strange beyond imagining. It's quantized, discrete, pixelated at the most fundamental level. It exists in quantum superpositions until observed. It's non-local, with distant parts instantly correlated through entanglement. It has finite information content, perhaps making it computable, perhaps even making it a computation. But it's also beautiful. The same quantum mechanics that makes reality pixelated also creates the colors of sunset, the sparkle of stars, the vibrant hues of flowers. The discrete energy levels of electrons create the entire palette of colors you've ever seen. The quantum nature of photons enables your vision. The pixelation creates the richness and diversity of the world. So yes, the universe is pixelated by light. But that pixelation isn't a limitation. It's what makes reality possible. It's what makes structure possible. What makes complexity possible. What makes you possible. You are made of pixels, quantum pixels, pixels of spacetime, pixels of information. But you're not just any random pattern of pixels. You're a pattern that can wonder, that can question, that can seek understanding. You're a pixel pattern that became aware of itself, and now seeks to understand the grand tapestry it's part of. And that, more than any specific scientific fact, is the real revelation. You matter. Your observations matter. Your questions matter. You're not an insignificant speck in an uncaring universe. You're an integral part of the universe's process of self-discovery. The universe spent billions of years evolving from quantum fluctuations to galaxies, stars, planets, life, consciousness, and you. It went from maximum simplicity to incredible complexity. And now it has parts like you that can look back at the process that created them and understand it, at least partially. So when you look at the stars tonight, remember, you're not just seeing distant balls of gas. You're receiving photons that have traveled across space and time to reach you. Each photon is a quantum bit of information, a pixel in the cosmic picture. And by observing them, you're completing their journey. You're fulfilling their purpose. you're participating in the universe's self-observation. Is the universe pixelated by light? Yes, but more importantly, the universe is illuminated by light. And you are part of that illumination, both the source and the receiver, both the pixel and the observer of pixels. Thank you for taking this journey with me. Thank you for spending these 3.5 hours diving deep into one of the most profound questions we can ask. If this video changed how you see reality, please share it with others. Leave a comment sharing your thoughts, your questions, your reactions. And subscribe if you want more content that takes science seriously while maintaining a sense of wonder and awe. Remember, you're not separate from this pixelated universe. You are the pixels becoming aware of themselves. And that's a beautiful thing. Until next time, keep looking up, keep asking questions, and keep marveling at the strange, discrete, wonderful reality we inhabit.